Okay, welcome to our lesson on crystalline structures, where we're going to learn about, if we look under the microscope at various types of materials, what they would look like on the microscopic scale and how that affects their material properties. In this lesson, we'll introduce a lot of information, a lot of topics where we won't go into great depth. I just want to introduce a variety of ideas about what aspects of the microscopic structure or microstructure of the material might be important to the material properties, and then later in the course, as we go into the various units on metals, ceramics, polymers, and composite materials, we'll learn about those effects in more detail. Okay, the microstructure of a material. Let's assume for a moment that we have a material that's in a liquid state. Perhaps it's in a liquid state because we needed to get it into the shape we need it to be in to form a dental prosthesis or some other device or component. And one of the easiest ways to shape a material is to heat it until it melts and then to cast it or inject it into a mold. And as the material cools off, it will solidify. And one of four things can happen when the melted liquid solidifies. The first thing that could happen is that one large single crystal could form. The entire mass of liquid could turn into one crystal. The second thing that could happen, and this is what usually happens, is that millions of really tiny microscopic sized crystals will form. The third thing that can happen is that if it's a material that has difficulty getting its atoms into the proper arrangement for its crystalline form, and it's cooled rapidly, too rapidly for the atoms to get into those positions, then it will remain amorphous. It will become solid, but it will still have same structure that it had when it was a liquid, essentially. And then the fourth thing that can happen is that we can have a mixture between polycrystalline and amorphous material. That's also very common to have some amorphous, or as we call it, a glass material, and then to have some crystals embedded within that on a microscopic scale. Now I'm showing here a picture of a single crystal. In this case, something looking like a gemstone, but the purposes of single crystals go beyond jewelry. For example, this is a synthetic sapphire material I'm showing here. You can read the words on the page through the sapphire because it's a single crystal and it doesn't have any boundaries between microscopic crystals in it. When those boundaries are present, like in this disc in the middle here, that's also made of sapphire crystals, but now instead of one crystal, it has millions of microscopic crystals, and they have grain boundaries in between the individual crystals that scatter the light slightly. You can still read the words through it. And these have important technological applications. Polycrystalline sapphire is used sometimes as a dental restorative material. This particular material is used to make light bulbs for the really hot sodium arc lamps that are used as light bulbs over highways. And the single crystal sapphire is used, among other things, as a protective window and armor for missiles in warfare to let their guidance systems see through the window, but to protect them from being sandblasted by debris as airplanes fly through air with dust and sand around them. And both of these materials are used to make orthodontic brackets for dentistry. Now the pictures on the bottom of the slide, I'm showing you for a polycrystalline material the wide variety of sizes that we can have. And so the microstructure here on the left is a microstructure of a metal, showing in different light and dark bands the various crystals in the metal, and you can see the micron bar shows the size of 200 microns. So most of these crystals are larger, a little bit larger than 200 microns. So that's a figure from your book, but the figure on the bottom right is one that we actually took on the microscope in our laboratory. We have an amazing quality electron microscope in our laboratory that can do things that very few in the world can do. And so if any of you are interested in doing research projects, then you'll get a chance to use that. It's a lot of fun. But Dr. Roach took this picture for us, and that is a material that's the strongest material we have available to make prosthetic teeth out of in dentistry, the strongest ceramic material we currently have, zirconia. And you can see that this bar is only 5 micrometers at this magnification, and that puts all of these crystals well below the 1 micrometer size, so they're in the nanoscale range. And that has an important effect, it turns out, on the material properties, that if you have really tiny crystals, what we call a fine grain structure, shown here, then you will have a stronger material. And if you have the larger crystals, what we call a coarse microstructure, then you tend to have a weaker material. Okay, I want to mention to you that there are a lot of different types of crystals that you can have. We have cubic shapes, hexagonal shapes. When I say cubic, what I mean is that if you take a cube and you put one atom on each corner of the cube, that's the arrangement the atoms form that type of crystal in. We have hexagonal structures, tetragonal, rhombohedral. There's a bunch of other structures listed in your book that I haven't included on the slide here. And then what's more, each of these types has several subtypes within it. For example, we have a type of cubic structure that has, in addition to the 4 corners, it has one atom directly in the center of the cube. We have, that's a body-centered cubic, face-centered cubic structure, has an additional atom on each of the 6 faces of the cube in addition to the corners. So we have a wide variety of structures that the crystals can come in. And let me back up here and mention that some of the crystal structures are longer in one direction than they are in the other direction, and so they have a different spacing between the atoms, and they will have a different property in each direction. For example, they will often have a different stiffness or a different coefficient of thermal expansion in the different directions. And it turns out sometimes this matters. For example, if all of the crystals in a component, an item, are all pointed in the same direction, like in this block of ulexite on the left, these crystals are all oriented in the same direction. And because those crystals have different optical properties in the 2 directions, then we see the rock has different optical properties in the different directions, and it'll likely have different coefficient of thermal expansion, different strength, different stiffness. And that's what we call anisotropy, is if we have different material properties in different directions. So common to fibrous materials, a lot of fiber composite materials, very common in biological systems like tooth, enamel, dentin, and bone materials, which have fibrous crystals in them. And the opposite of anisotropic, of course, is isotropic. And you can have, isotropic would be having the same material properties no matter what direction of the object you measure the material properties in. And that can come about by two ways. One is that you can have crystals that are randomly oriented. So you have lots of microscopic crystals in the structure, and they're random in orientation. So yes, for each crystal it's anisotropic, but for the entire object, the properties, the material properties of the crystals average out over all the directions, and the object is isotropic in properties. And then the other case would be if you cooled the material too rapidly and it couldn't form any crystals and it remained amorphous. Amorphous or glass materials tend to be isotropic in material properties. And so we're bringing back this nice microstructure of zirconia that we have on the right side. And I want to point out that the crystals in the micrograph don't have different colors just to distinguish them from each other. They have different colors because they're color coded according to which side of the crystal is pointed at the camera in the microscope. And so by the variety of colors, you can see that they have all different orientations at random through the structure. So that's the most common case for most materials, is to have a random microstructure. Okay, let's talk about the types of structures that we have for our three major classes of materials, our metals, our ceramics, and our polymers. In a metal structure, you'll have the atoms arranged as shown here, and we can look at that structure and try to find the smallest repeat unit that we can translate over in the structure, and that it will be equivalent to the original position again and again. And that smallest repeat unit is highlighted and then shown separately on the left, and we call that a unit cell. Okay, so that's the most elementary repeat unit of whatever the structure is. And on the far left, the same unit cell is shown as in the middle, except it's just drawn differently so that the atoms accurately fill the space instead of being small to make it easy to see where their centers are. And you see that it looks like some of the atoms are cut to form an eighth of an atom, because their center is located on the corner of the unit cell, which means that each of those atoms on the corner is shared with several other unit cells, and only 1/8 of the atoms lies within this unit cell. The other thing I wanted to tell you about that is, in metals, we typically have the most densely packed structures that it's possible to have. And so we call this, there's two very common structures for metals: face-centered cubic structure, which I mentioned before, and we abbreviate that FCC, and then hexagonal close-packed structure. Okay, and we abbreviate that HCP. Those are both as tightly packed as you can get if you have objects that are spherical in shape and all exactly the same size. And it's not all that tightly packed. It's you may be surprised to find out that it's only 74% packed. So we have what we call for each structure the atomic packing factor. And for our close packed structures, that's going to be 0.74 or 74% of the volume in this unit cell is actually occupied by atoms. And that leaves 26% as empty space, or what we call free volume. Okay, and in this course, we are not going to go any deeper than that. In our more advanced course at the graduate level, we spend a lot of time looking at the individual structures and calculating their various packing factors and the theoretical density for the materials, because those are important properties to know when figuring out better ways to process the materials. But we won't make you go through all that geometry in this course. It's beyond the scope of what you need to know. I do want to call your attention to the fact that the packing factor is important for more than just metals. It's any type of system where you're trying to pack particles. So eventually in this course we will cover suspensions of ceramic particles in water and processing those, packing those together. We will cover suspensions of ceramic particles in polymer resin material, and which is one of the most prevalent materials used in dental restoratives. And so how tightly you can pack together objects that are roughly spherical, whether they're all the same size or whether you have different size distributions, is going to be an important area of material science. Okay, so let's look at the ceramic structures. We see that this is a two-dimensional section through a unit cell. So this is the way your book is drawing for ceramics, but actually you have the same unit cell that you would have in the case of a metal for most ceramic structures, except that because a ceramic is formed by a reaction between a metal cation and a non-metal anion, then we will have a mixture of two different types of atoms with two different sizes. And remember, before we talked about the size of the relative radius of the ion determines how many anions can fit around a cation, the coordination number, that type of thing. Typically in the ceramic structure, we will have the anion, the negatively charged ion, in the lattice sites that would be occupied by atoms in a metal structure. So in the corners of the cube, sometimes in the faces of the cube also. And then in between them, we will have the positively charged ion or the cation. So I'll put some charges in there to illustrate for you. And typically our anion is going to be oxygen. And then we will have some metal for the cation, and it's usually the case, it's never the case that the cation will be smaller than it needs to be to fit in between the anions. If it is, it will go somewhere else in the structure to a smaller crevice. It's improbable that it will be exactly the right size to fit within the whole while the anions are touching each other along their radii. So this is the most common case that we have for ceramics, where the metal cation actually pushes the anions apart slightly, and so ceramics don't have close packed structures, even though the structures look similar to metal structures. So this means ceramics will have lower density than metals on average. Lower density because they have more free volume, and also lower density because they have lighter types of atoms. The metals have metal atoms, and the ceramics have some metal atoms, but they also have a lot of oxygen, which is fairly light compared to most metal elements. So we have two reasons that ceramics tend to be less dense. Now, moving on to polymers. Polymers, or an example of a type of polymer, would be the materials you know in lay terms as plastics. And these are structures with carbon in the backbone. These carbon atoms are connected to each other in a long chain, much longer than we can show on the screen here, drawing to scale. So the chains, they can be short, but they're typically in the length of millions of carbon atoms connected together. And they have hydrogen atoms or some other atoms sticking off the sides. And those chains will crystallize by folding back on themselves with the type of pattern that you see here, forming crystals. And you can imagine it's difficult for them to get into that arrangement. We said that ceramics sometimes have a lot of difficulty getting their atoms into the proper places when they're being cooled rapidly, and so they are more likely than metals to form amorphous solids. Well, polymers even more so. Polymer is a complicated structure. Even in the case where the polymer is linear, it's difficult for it to get into the proper conformation here. And in many cases, we have some type of large group which is hanging off the side every once in a while that prevents the polymer from tightly folding back on itself. Maybe even these large groups are coming from different sides at random. And so it's really common for the polymers to form a mixture of crystal and amorphous, even being mostly amorphous materials. Okay, I want to talk briefly about the concept of the close packed planes and the close packed directions inside a metal crystal, because that's going to be important when you learn about mechanical properties of metals later. We have some example crystals here. This is not a space filling model on the left, but it's the same crystal structure as shown in part B. What part B is it is a diagonal cross section through this face-centered cube. So I'm drawing the lines there are going to be the same as the red lines that I'm drawing in part B. So that's the cross section we get if we cut through the diagonal of the cube. And well, I've drawn that too large actually. One cube is right there, is that size. And you notice on the space filling model that the atoms are all touching each other along this direction, but they're not touching each other along some of the other directions. It turns out that when atoms are touching each other along a direction, it's more easy for the crystal to deform and the planes of atoms to slip past each other under mechanical force. And so that's going to control what we call the critical resolve shear stress that you'll learn about in the metal section of the course. And we have different crystal structures that will have a different number of close packed directions. For example, this other crystal structure, if we take a cross section diagonally through, this is body centered cubic, this is face centered cubic. In the body centered cubic, that's the cross section that we're taking, and you notice that instead of a horizontal close back direction, it has diagonal close back directions, and it has two of them crossing each other. And so this is going to be important for determining which materials are easy to shape, to polish, and which ones will quickly turn hard and brittle if you try to work with them at room temperature. And there's just an example of a piece of metal that has had some tension applied along the length of the rod, and the rod did not break with a horizontal fracture as you might expect with the force applied in that direction. Instead, it slips along a plane where the atoms are in a close packed arrangement with each other. Okay, I want to talk about systems where the same composition of material can have more than one type of crystal structure. So it's not always that just one type of crystal goes with each composition of material. We often have multiple of what we know as allotropes, different crystal structures for the same composition, and usually those come about because of changes in temperature, heating or cooling the material. Pressure can also cause a shift in different type of crystals. So I have the phase diagram for steel here, our steels and cast irons in this system. We have mixtures of iron on the left and carbon far to the right there. And the vertical axis is temperature. So as we go to the top of the chart, we're going to higher temperatures. And at room temperature, we have one crystal phase, we call the alpha phase or ferrite. And actually there's two crystal phases, ferrite and cementite, mixed together with each other. And as we heat the material, we go through a temperature where it transforms to a different allotrope. And these two phases of, and I'm using phase to refer to a distinct crystal structure within the microstructure of the material. That's an important vocabulary word for you there, phase. And as we heat, we go through a transformation temperature above which we have a gamma phase. And then if we continue heating the material, if we're over here on the left side of compositions, we'll actually reach this tiny area where we have yet a third allotrope, different crystal structure. And then if we keep going, we enter this region, which is liquid. Anywhere at those really high temperatures, the steel will melt to form a liquid. And upon cooling, if we cast it, then we will transform back into the low temperature phases. However, there are different types of transformations that occur depending on how close the allotropes are in structure to each other. So for example, in steel going from austenite to ferrite, we have what we call a reconstructive transformation. And that means there's a really big difference in crystal structure between austenite and ferrite structures. You can see here with the atoms on the faces and here with the atom in the middle. So it's called reconstructive because the atoms really need to move around a lot and totally reshape the structure. That means it's going to be a slow transformation. In the case of steel, if you cool it quickly, you do not get ferrite. You get a different structure. You get a martensite structure which will remain unless you give it heat and give it time to transform into the structure that it was supposed to be in. And so sometimes you get the structure that is what we call the equilibrium structure, and sometimes you just get a structure that's easier to form. Structures that are easy to form are what we call displacive transformations to form those structures. It's where there's very little difference between the crystal structure that we are starting from and the one that we're turning into. Frequently, the difference is caused just by stretching in one direction, like having the structure go from cubic to tetragonal, which is like a cube but a little bit longer in one direction, or just shifting the structure on one axis, shearing it over. Um, very small changes, these transformations can happen rapidly even when they're not um, the equilibrium reaction that's supposed to happen. And some of these are very important to dental materials. For example, this shear displacive transformation happens in the superelastic nickel titanium alloys that we use in some orthodontic arch wires and give it their superelastic properties. And the dilatation transformation occurs in the ceramic zirconia or zirconium dioxide, which is the toughest ceramic that we have available to make dental restorations out of currently, and it is the change in shape of the crystal upon cooling that's responsible for the zirconia being so tough. And we'll talk more about that in the future. I just want to make you aware that changing the atomic packing factor, changing the free volume as we change the crystal structure in an allotropic transformation can have some serious side effects. So this is the case of a metal that has a very large change in its atomic packing factor when it cools off, and well, I don't remember if this expands upon cooling or heating, but it changes one way or the other, and such a large change in free volume actually causes the material to fracture and crumble to pieces. And this is also the case in that tough material I mentioned to you, zirconia. You may have seen advertisements for fake diamonds, cubic zirconia, and that's a similar material. It turns out if you take pure zirconium oxide and cool it off from processing it in a furnace down to room temperature, it undergoes a slight, just a 4% increase in the size of all of its crystals when they transform to the room temperature phase, and that is enough to make it crack and fall apart. And by adding impurities such as yttrium to the material, or sometimes calcium or magnesium or cerium, we can cause some empty atomic sites in the structure, some vacancies, which can accommodate that desire for the material to expand and to keep that from happening so the material doesn't fall apart. So when you hear cubic zirconia as a fake diamond, cubic is the high temperature form of zirconia, and it means that they've added a material to the zirconia to keep it in its cubic structure even at room temperature. Okay, so we have all these different type of crystals, and what crystals we have and how much of each type we have are controlling our material properties. So obviously it would be good if we had an analytical technique for measuring crystallinity and identifying crystal types, and we do. It's called X-ray diffraction. And way X-ray diffraction works is that we bounce X-rays off of the surface of the material. And these atoms are arranged in crystal planes down here. Okay, so some of the X-rays bounce off of the top plane, some miss the top plane and bounce off of the next plane. And the ones that bounce off of the lower planes within the structure before they come out, those will travel a longer path than the ones that bounce off of the top. Those X-rays, because they traveled longer before they reached our detector up here, they will shift, and their vibration may be in phase or out of phase with the X-rays that reflected from the top. And if they happen to be in phase, that's this top case here, where the peak of one X-ray still lines up with the peak of the other X-ray, and the trough lines up with the trough. And if they each have an amplitude of A, then when they are added together and the detector views them, it will see an X-ray with an amplitude of 2A. So they have really high intensity if they come in phase. And we call this constructive interference. Okay. Now, if they are out of phase with each other, then we have what we call destructive interference. And that's where the peak of one X-ray lines up with the trough of another, and the trough lines up with the peak, and they cancel each other out, and the detector sees basically nothing. And so whether they're in phase or out of phase will depend on the type of crystal you have, which controls the distance, what we call the D spacing, between the atomic planes. Oh, I can write that on should write that on the next slide. So this is our D spacing. This space in between these planes is our D spacing, and so on. And so each D spacing will have a different angle of reflection that it causes constructive interference at. And as you can see depicted here, the same crystal structure can have several different types of planes in it, and each one will have a different D spacing. So each crystal has multiple D spacings associated with it. And if we scan the crystal over a range of angles to theta and look at the intensity of the X-rays that we're detecting, whenever we see a large peak, that's constructive interference. So that tells us that we have D-spacing that is producing X-rays in phase with each other there. And we will have a variety of D-spacings, and when we search through the computer, it matches that combination of peaks with a certain crystal type. And we can have mixtures of more than one type of crystal, and the computer can calculate for us how much of each type of crystal we have. Okay, I also want to cover briefly how these crystals are produced in the first place. So these figures from your book are meant to indicate that we have a melted liquid, it's cooling off, the liquid reaches its melting point or freezing point, same thing, and then the liquid wants to begin to transform into a solid material, because below the melting point, a solid material is favored energetically. So if the liquid turns into a solid at those low temperatures, it will release some energy for the system. And so there's a driving force for that to happen. Some nuclei of crystals form within the liquid. This isn't, turns out, automatic. We'll talk on the next slide about how that happens and when. And then once the nuclei form, then they can rapidly grow and each of them becomes larger, and eventually they grow to confluence and impinge on each other. Okay, so how do these nuclei form? How does the crystallization actually get started? Um, well, it turns out that the material would like to anthropomorphize it. It would like to be in a solid state when it's below its melting point. There's a certain amount of energy that we get back from it for every unit volume of material that transforms into the solid phase that it's supposed to be at that temperature. So if we consider that we're trying to form a nucleus of solid material that's spherical in shape, and that's going to be produced within the still molten liquid surrounding it. And producing that sphere will have a certain volume associated with it, which is related to the radius of the sphere cubed. And it will also have a certain surface area. The surface area is opposing the transformation because it turns out that whenever you have a surface between two different materials, even if they have the same composition and it's just a solid and liquid, or it turns out even in the case between two solid materials of the same composition, you have some higher energy associated with that surface being there between them. And so the volume wants to give us back energy by transforming. The surface of that sphere is opposing that from happening. And the amount of energy that's opposing the transformation is proportional to the surface area of the sphere, which is a function of the radius squared. So plotted here in red is the surface energy, which is opposed to the crystallization, and plotted in blue is the volumetric energy recovered, which is in favor of the liquid crystallizing. And when those get added together, whether they sum to zero or not tells whether or not that nucleus is going to form and be stable. So shown in green here, and I'm highlighting it in red, is the sum of those, the free energy or change in chemical potential that we get from that transformation occurring. And it turns out that we have an energy barrier which is associated with a critical radius r star. So if the atoms in the liquid are vibrating and they vibrate together in the form of a solid crystal that has a radius of r star or larger, then that crystal nucleus will be stable and will remain. And if it's smaller than r star, the critical radius, then it's not stable and they will dissolve back into the liquid. And so that takes some time, and it has to be at the proper temperature. It turns out that materials will not crystallize exactly at their melting point or their freezing point. There's not enough chemical potential drive to overcome that surface energy. And so they actually go to a little bit below their freezing point before they start to crystallize. And how far we take them below their freezing point, how quickly will determine the number of crystal nuclei that form, and that will control the size of the crystals that form eventually. And as we mentioned before, the size of the crystals controls the optical properties, the strength properties of the material. And you'll get into all of that in more detail in the next section when you go over metals, properties of metals and phase transformations. Okay, the last thing that I want to talk about in this lesson are the defects that can occur in crystals, because those also affect material properties and how easy the materials are to process. And the first type of defect that we have in crystals is that we can have a vacancy or a hole where an atom is missing. And we can also have an atom from the same material that's in a place where it doesn't belong, a self-interstitial site. And it turns out that the vacancies are really important because those will control how mobile the atoms are through the structure, how easily materials can diffuse at high temperature when you're processing the material in the furnace. And so if these vacancies are there, then it can make the material much faster to process. And just because I think it's really neat that we have such high magnification microscopes in material science, I've included this other figure from your book that shows the surface of graphite under 7 million times magnification. And you can see the vacancies of the missing individual atoms there. Okay, another type of defect that's very important in crystals is that we can have impurity, either a small one that will go into a hole in the structure, some of the free volume of the structure, and sometimes it's just large enough that it slightly pushes the neighboring atoms apart. And when it does that, that's important. That causes a strain in the atomic lattice and can really make the material much more hard and stiff. And we can also have the case where we have in metals an alloy between two different metals that have very similar size to their atoms, but they're slightly different. A famous example is copper and nickel, and you can get the foreign atom in there, and it also causes a strain in the lattice because of the slight difference in size. And another important, maybe the most important type of crystal defect we have are called dislocations. And a dislocation is a one-dimensional defect. If the point defects could be thought of as a zero-dimensional defect, this is a defect that makes a whole line in the structure. So you can see here that we have a line of atoms that are missing. We have in this space 3 lines of atoms, and in this plane of atoms below we have only 2 in the same space. So either you can think of it as having a extra line of atoms inserted, or we have a line that's missing. And so this is called a dislocation, and it makes it easier for the crystal to be deformed under mechanical stress. If you think of pushing here and pushing here with sheer mechanical stress and trying to shift one plane of atoms over on top of the other. To do that, you have to temporarily break the bonds and force an entire area of all the atoms in this surface past all the atoms in the surface below it. So a two-dimensional area. However, if we have this dislocation in place, and we try to shift over the atoms that are between those planes with the dislocation, then because of that, this line of atoms can shift over and it can bond with this line of atoms. So it can shift over and become next to it, and then that will leave this line of atoms as being the one that's extra and doesn't have a line below it bonded to it. So we shift them over one row at a time, and it takes a lot less force to cause that to happen. I like to think of it as if you have a very large area rug in a huge ballroom, and you need to shift that 5 feet to the left. And if you're going to drag it 5 feet, then you need to get a team of people, several people here, to grab that rug and pull as hard as they can and try to slide it 5 feet, because you have to overcome all the weight and all the friction of the rug all at once on a two-dimensional area. However, another way to do that is to put a small wrinkle in the right side of the rug that runs down the rug, and then to have just kicking that wrinkle so that travels down the rug, and then you move the entire rug over by a little bit with just a tiny bit of force every time you move that wrinkle down the rug a little bit. So that's what a dislocation does, is it makes it so that we're only overcoming the force of one line of atoms at a time. So it's a much lower force. And it turns out this is what allows metals to have malleable properties, to be ductile materials, and this motion doesn't happen in ceramic materials, for example, even though the dislocations are there, because for reasons we'll go into in the future, the dislocations aren't allowed to move through ceramic crystals, and that's why ceramics tend to be very hard and brittle. Okay, grain boundaries are the last type of defect I want to talk about. That's where different crystals have grown to confluence. So you have one crystal here, and you have another crystal there, and you have a third crystal here, and each one has started from its own nucleus upon cooling the material from the liquid, and the nuclei, crystal embryos, grow until they meet along these lines. Okay. And you notice along those lines, let me come back and erase some of that so that you can see it better. You notice along those lines that the atoms appear more disorganized and there's some extra free volume there. So you can consider those to be vacancies. They enable bits of the material, impurities, to be conducted very rapidly through the structure along those grain boundaries compared to through the bulk of the grains, and that affects the processing in the case of ceramic materials. In the case of metallic materials, we can consider neighboring grains. We have, for example, on the right here, we have two neighboring grains that have slightly different angles of their atomic planes with respect to each other. And at the grain boundary where they meet, essentially the vacancies every once in a while are forming a dislocation. We can consider that grain boundary to be a row of dislocations. And this will be important when we talk about working a metal until it turns hard and brittle, and then heating it up to anneal it and make it more ductile again, and what that does to the crystalline structure, how it the dislocations move to the grain boundaries, and they will actually divide up the large crystals to make smaller crystals, and that changes the material properties, as you'll see later on. The last type of aspect of grain boundaries that I want to talk to you about is when you have a grain boundary that acts as a mirror image of the crystal. So along this twin plane here, the different crystals on either side of that twin plane look like mirror images of each other. And that typically happens when you have a crystal that has a mechanical force applied to it while it's hot, and the force was not applied during the original growth of the crystal, and then the crystal can twin to relieve that mechanical force. And some studies that have been conducted by Dr. Roach the past few years on our campus have uncovered that in medical implants, when you have a twin boundary the angle between those crystals along that twin plane is really inopportune, and it's the exact angle that lends itself to nucleating fatigue cracks and making the medical implants not last as long before they fail. And here's another example of grain boundaries I forgot I was going to mention to you, is the grain boundaries can actually, even in the case where they're not twins, if they're large enough, long enough grains, those can serve as defects and be a site where a crack can nucleate. And this is an example of a metallic material that's been cast as a liquid into a mold, and the crystal nuclei were having difficulty forming within the liquid, and the walls of the mold gave them a place where they could form a solid on top of another solid material, the wall of the mold being the second solid material. And so lots of crystal nuclei form along the walls of this mold. You see all those little tiny crystals in there, and not many crystal nuclei want to form in the center, because that's forming a solid out in the middle of the liquid, and there's a large surface energy associated with doing that. So instead they form on the solid wall, and then they all begin growing towards the center, eating up the liquid as it cools, and that creates really large crystals, and it makes for a weak material. Okay, you may want to go into Callister's book and Anna Savage's book again and read the chapter that we have on this material. However, I wouldn't recommend it. If you like to see those figures in context in the order they come in the book, that's great. But the last lesson we had, I mentioned to you that for that lesson, the material in the textbook was almost identical to what I was presenting in the video. That is not the case here. For this chapter, your textbook contains a lot of information that you do not need, that's beyond the scope of what a dental student needs to know. And so I've covered just a small amount of the information in this video. And so if you go to the book and you do see a lot of topics that I didn't cover in the video, then please don't worry about that.